Hold on just a second. Okay, so first let's talk about the homework problems. Okay, so last time I assigned two homework problems in the chapter 4. That's number 8, number 9. So we'll begin to talk about this homework first. Now, number eight is about the uniform convergence of sequence of continuous function. So this is the last subject we talk about in chapter 4. So here we have a sequence Fn. Okay, they are all continuous function and converge uniformly to F. Now, then we have a sequence of points, so called Xn, in the domain D, which is converging to X star. Now, then we are going to form a sequence of points by letting Fn acting on Xn. So Fn and Xn give you a point. So basically, now I have a second sequence of points. Then we're going to show that the limit of this equals to Fx star. So that's a properties. So this is something related to the uniform continuity or the uniform convergence of sequence of continuous function. Okay, so let's see how we can prove this. So we're going to achieve this by using the epsilon n argument. We're going to show the limit, the limit Fn Xn equals to Fx star. So given epsilon greater than 0, now first we use the fact that Fn converges uniformly to F. So based on the uniform convergence concept, this means that for this epsilon, and there's a large n, now when n large enough, then you can see the Fn minus F will be uniformly smaller than epsilon divided by 2. Okay, why divided by 2? This is because this is a technical reason. So this is a uniform control between Fn and F. So this is true for all x indeed. Okay. Now let's note that our uniform convergence, okay, for Fn implies that F itself, the limiting function, is also a continuous function. And now I have a sequence of point Xn. So now I'm going to relate that sequence with the continuity of the limiting function F. So again, given epsilon greater than 0, then you can see that since F is continuous, though there is a delta, such that when x minus x star is less than delta, that means when x is very close to x star within delta distance, then fx minus fx star, the distance will also be less than epsilon delta 2. Now I achieve two different inequalities. So how I can combine these together. And so we're going to now, given this epsilon, we're going to let x minus x star to be less than delta. And then we're going to have the critical estimate. So now you are taking difference between Fn, Xn minus Fx star. Now these things can be, you can insert a middle term, Fxn, okay? Then you use triangle inequality. So you can break down into, you can estimate this by Fn, Xn minus Fxn, and plus the second term is Fxn minus Fx star, okay? And so both terms are estimated above already by epsilon divided by 2. So you add this together, you can see that this is actually less than epsilon. So this shows that the Fn, Xn minus actually goes to Fx star. So that's a proof. So this proof is basically use the concept of uniform convergence and also the continuity of the limiting function. Okay, so that's number 8. So therefore you get the result. Now number 9 is interesting. Number 9, there's if you look at the problem, you can see that there's a two places involved. and mention the uniform. So first you have a function f, which is uniform continuous function on the entire line. Okay, on the entire line. So this is the one assumption. And then from this uniform continuous function, I'm going to construct a sequence of function called fn by adding 1 over n to the x. Okay, it looks like fn is a composition function from original fx. Okay, and so fn is a new function. It's built from, it's basically a shift by distance 1 over n of the original function fx. And now we're going to show that fn actually converges uniformly to f on R. So here you can see the second uniform, the word second also is pure uniform, but this uniform is different from the first uniform. The first uniform is talk about uniform continuity. Okay, and now the second uniform mentioned is about the uniform convergence of sequence of functions. So these two, although the same words, but however, these uniformly meaning differently, okay, has different meaning. Now the proof of this is very simple, it's direct consequence of uniform continuity conditions. So given epsilon greater than 0, now first we notice that f is uniformly continuous on R, okay? So there exists delta such that when x1 minus x2 less than delta, then fx1 minus fx2 is also less than delta. So that's because of the uniform continuity, right? Now, then I'm looking at the difference between x and the new shifted point, x plus 1 over n, okay? And you can see that the distance obviously equal 1 over n. Since I'm choosing n is greater than 1 over delta, so 1 over n, the distance now is less than delta. So this means that fn minus f is really the difference of the same function at a different point differed by 1 over n. Now it's also less than delta. So therefore, this shows that, so everything reduced to the fact that f is uniformly continuous. So this shows that the sequence of function fn actually converges uniformly to f or R. So this is another problem, the number 9. And number 9 can be changed slightly, replacing 1 over n by any. So you can, instead of using 1 over n to construct the fn, you can use any sequence. I mean, suppose you're given a sequence goes to 0. So you can replace that sequence, replace 1 over n by the sequence. You can create a different fn, right? Then the same result applied. Okay. All right, so this is about the number 9. So that's the first things I want to talk about the these two homework problems. Okay, and now we're at a position to continue on chapter 5. Okay, let me stop sharing here. And hold on just a second, okay? There's some chat. Okay, so now let's work on the chapter 5. Okay, and so let me see any questions. Okay, no question. That's good. All right. Now, chapter 5 is about it's a differentiation. Okay, it's about differentiation. It's very different. So that's the last chapter, and so you can see. So this is the last chapter we're going to study, and basically this is a short chapter. We can handle it in maybe in 3 lectures. Okay, we handle this in 3 lectures, and so this is called a differentiation. This differentiation in R. So we're returning to the one-dimensional Euclidean space, not a multi-dimensional space. Okay. Now, if you continue on 640, then you'll be able to study differentiation in RP. That's a multi-dimensional differentiation. Now, in this chapter, in this class, we only talk about the differentiation in the one-dimensional space. Okay, so now the material here I'm going to present it is maybe it's not new for you because you have all taken this calculus series. Okay, so in the calculus 1, you have already studied derivatives, almost everything I'm going to cover here. But however, in this chapter, what we are going to do is not just repeating the calculus material, but also we are going to study deeply the proofs behind these theorems. Okay, now first we're going to talk about the derivative. So this is the most important concept in calculus. Okay, the derivative. So in the following, we shall consider a scalar function. Okay, f. So sorry, this shift of the word. It's a function f defined on an interval in R. Okay, so 5.1 we want to talk about the derivative definitions. So let's consider a function defined in AB. Normally, I mean, this interval has to be an open interval. But however, I include it as a closed interval. This means that in some sense, you can also define the derivative at endpoint. So when you define the derivative at endpoint, you are taking the halfway limit, not a full limit, okay? But don't worry about it. You can just think about, I have interval, the function is well defined, and I pick a point from this interval. Now we say a real number L is the derivative of f at the point C. What does it mean? It means the following statement is true. This means that for every epsilon greater than 0, there is a delta epsilon, okay? Such that if x is sufficiently close to C, okay, the x now x cannot be equal to C, okay, but however x is close to C, and this within delta distance, then the ratio fx minus fc divided by x minus c. So that ratio, okay, minus L, the distance is less than epsilon. So if this condition is satisfied, and we can say that L is the derivative of f at c. Now this looks like a complicated, so abstract. But however, what does it really mean? Well, I'll show you the actual meaning later. But suppose here, let's say the function is differentiable, I mean, at C. So what does it mean that derivative exists at this point? Okay, and so what does it really mean is that the limit, so if you look at review the limit concept, you will see that this is actually saying that the ratio, the limit of ratio when x goes to C is equal to L. Now this ratio this limit cannot be evaluated by substitution, because suppose you substitute x by c, okay, and then you will have fc minus fc. On the top you get 0, the bottom also 0. You have 0 divided by 0, so that ratio doesn't exist. So you have to use a limiting process with x not equal to c in the process, okay, to this. So if this limit exists equal L, so we can say that the f is differentiable at C. And here the notation is f prime stands for the derivative. While you can have a different notation, you can call this derivative is df dx, or sometimes dy dx. Okay, they're all different kind of notation, but corresponds to the same concept here. Okay, now the derivative, the first important application of derivative is that it's a geometric application. Now suppose you have a curve, okay? So you fix a point x naught, okay, so that's a p naught. So the derivative, what I mean by the derivative of the function at this point that's corresponding to this curve, this basically is mean something related to the tangent line. So you can through this curve. Now this curve is a very smooth curve. You through the point x naught at this started from x naught, on the curve is p naught. So at this point you can draw a straight line. That's a tangent line. Okay. Now the derivative actually related to this tangent line. Okay. Now here I'm drawing the second point. P is away from x naught. So the P. Now if you're connecting P naught and P, then you will get what we call the secant line. It's called the secant line. So as the P approach to P naught, or x naught plus delta goes to x naught. Or suppose these 2 points are very close to each other. Then the secant line will gradually become the tangent line. Okay, will gradually become the tangent line. So the slope, the derivative actually corresponds to slope of the tangent line. Okay, now what is slope? What I mean by slope of a tangent line? I mean, tangent line is a line. Slope of this line basically is a tangent of the angle. Okay, the angle. That's the slope. That's the geometric meaning of the derivative. Now, if we look at this picture, and also you can see that if we take the ratio, okay, fx minus x naught divided by x minus x naught, and then you can see this basically corresponds to the slope of the secant line. Okay, if you can and look at and fx minus x naught corresponds to delta x. That's the difference of height. And then divided by x minus x naught, that's the difference of the x, that's delta x. So delta y divided by delta x, that's exactly the tangent of the angle. Okay, that's the slope of secant line. Now, as we move x towards x naught, you can see this slope of secant line will gradually become the slope of tangent line. That's the limit or the derivative of the function of this point. Okay, so this is the geometric meaning of the derivative, but the derivative also apply to some physical term, like if you want to calculate the velocity and the speed, something like this, and they're all related to the derivative. So anything related to like change of ratios, okay. So this was related to the derivatives. Okay, now first theorem, and 5.2, we'll talk about the theorem. Now the first one is the continuity theorem. The continuity theorem basically saying that in order for a function to be differentiable at this point, then the function needs to be at least continuous at this point. So the having derivative or differentiable at a certain point is a more strict condition than the continuity conditions. Okay, so this statement is like this. Now, if f has a derivative at c, and then f is continuous at c, okay? So we're going to prove it. Now, proof is very simple. And also at the same time, I'm going to review some of the old concept. Now, since f has derivative at c, so I can apply the definition. So there exists a delta epsilon. So here, now I'm choosing epsilon equal 1. Because in the concept, you can choose any epsilon. Now, for our purpose, I only need to choose a special epsilon. Okay, the value is not so important. So I can pick epsilon equal to 1. So for this epsilon, there is a delta, okay, such that when x minus c is less than delta, then the fx, the ratio minus the derivative, I know the derivative exists, okay, it's less than 1. 1 is epsilon, okay? Now from here, I use the second kind of triangle inequality. So remember second kind of triangle inequality, okay? So you'll get the fx minus fc, the ratio itself, the absolute value of the ratio, okay, is less than 1 plus the absolute value of the derivative. Oh, sorry, here the derivative should be at c, okay? at C. So you can see from the left side, there's f prime C, so the right side should also be f prime C. So this is important. So now the right side is controlled by, is a fixed number. It's just 1 plus f prime C. On the left side, x is variable, still vary, but the whole thing is controlled by fixed point, okay? So this will imply that then you multiply x minus c on both sides. So you can see that fx minus fc is less than 1 plus absolute value of the derivative at c, the whole thing times x minus c. And this will give us the continuity, imply f is continuity. Okay. Now, if you remember in the last chapter, we have a homework problem. Okay. And that's correspond to the homework problem actually. But however, I choose to review that solution with you. Okay. So how do we see that this will imply that f is continuous at c? So let's call the right side, the fixed constant 1 plus f prime c to be L. Okay, call this as L. L is now a fixed constant. So the inequality looks like this. Fx minus fc, the absolute value is less than L times x minus c. Okay, and this is actually what imply the continuity. Why? Because for any epsilon greater than 0, you can simply choose the delta equals epsilon divided by L. L is a fixed number. So when x minus c is less than delta, so you can see fx minus c, okay? And so this difference is less than L times x minus c. So this is what we have. Now, this is controlled by L epsilon, okay? That's x minus c. Times L, then times epsilon divided by L. So 2L cancel, which give you epsilon. So you can see that fx is continuous at c. Now this kind of continuity can be considered as the strongest continuity. It's called Lipschitz continuity. I mentioned this in the chapter 4. Okay. So this is so that's the first theorem. So this first theorem tells us that in order for a function to be differentiable at a certain point, then the function needs to be at least continuous at this point. Okay. The next thing is 5.3. It's a group of theorem about the computation of the derivatives. So now let's say that you have two functions, f and g. They are both differentiable at c, meaning that they all have derivatives. Okay, then we have 4 formulas. So all these formulas, you learn this formula from calculus 1, but here we are going to prove them. So now if f and g are differentiable, then f plus g is a new function, is also differentiable at c. And also the derivative of f plus g should equal to sum of the individual derivative. Second part, if you times k to one of these functions like f, you're creating a new function called kf. K is a constant. Then this new function is also differentiable at c, and the derivative is equal to k times the derivative. Okay. Now the part C is the product rule you learned from calculus 1. So if f and g is differentiable, if f and g are differentiable, then f times g is also differentiable at c. And here is the famous product formula. F times g derivative equals to the derivative of f times g plus f times the derivative of g. Okay. Then part D is the quotient rule. Quotient rule, now we have to assume that GC not equal 0, okay? Then the f divided by g, the derivative is equals to this complicated formula. So I think you all know this formula. You remember this formula, okay? Now today our goal is trying to prove this formula using the new concept, okay? All right, so first let's see the part A. Part A is really simple. So, okay, so here we have that we need to show that f plus g is differentiable with this formula, okay? Now, our assumption is that for both function f and g, they are differentiable. So therefore, both limit exist or equal to f prime c and g prime c. So this is something we are given, okay? Now we're going to work from here. So in order to show f plus g is differentiable, we use the definition of the derivative. Using definition means that I have to compute the limit. So what is f plus gc? If it exists, it has to be the limit f plus gx minus f plus gc divided by x minus c, right? But this expression can be changed because f plus gx basically means fx plus gx. And the same thing for at c point. That is fc plus gc, right? So this expression can be reduced to the second limit. And the second one can be, first I can regroup. I can put f term together, g term together. So in the next limit, so what we have is fx minus fc as group 1. Then group 2 is gx minus gc. Okay. And then I can break using the limit property. I can break this limit into the sum of two limits. Okay. And right in the middle, I can break it into these two individual limits. And these two individual limits, actually, they are exactly equal to fc's, f prime and g prime, fc. So if you look at the left side, f plus g prime, now the right side is f prime c plus g prime c. So this actually proves our formula. Okay, so that's the proof of part A, which is really simple. And part B is similar. It's also simple. Because here, part B is that you just multiply by k, right? So I'm going to choose that kf prime equals to k times the derivative. Okay, again, by the assumption, I have this limit. And then I compute the kf derivative. Again, using the limit. So by limit, it means that kfx minus kfc divided by x minus c. Okay, but the kf is basically the product between k and f, right? The same as k and fc. So k can be moved out because k is a common term. So this can be written as k times fx minus fc divided by x minus c. And then you can see k is a constant, so you can move the k outside of the limit. Okay, now once k is moved out, you can see this equal to k times the limit of fx minus fc divided by x minus c. Excuse me. So this is exactly equal to k times the derivative at c. Okay, so this is the second formula we verified. So both part A, part B are very simple, the proof. The difficult part is C and D. That's the product rule. Okay. Now again, we begin with our assumption. Assumption saying I have two limits. Both give the limit, the derivative f prime and g prime. Okay. Now I want to investigate the product. So now I'm computing the limit with fgx minus fgc. Now fg is defined to be the product. So this limit can be written as fx gx minus fc gc divided by x minus c. So the key is that I have to reduce this product into individual limit. Okay, but the product makes some trouble. Okay, so what we should do is the following. I'm going to insert, you can see the red term, insert two equal terms which cancel to each other. Is fc and gx. They're all canceled. One is minus sign with the plus sign. Now by introducing these two terms, now I can see I can break in the middle of this limit. The first limit, you can see that the first two terms have gx is a common term. Okay, so then the expression can be written as fx minus fc times gx divided by x minus c. The second limit, you can see fc is a common term. So you can write it's fc times gx minus gc divided by x minus c. Okay? So this we are moving, making progress to reduce the individual limit. Now for for the first limit here, I can break this into two limits as a product because this is based on the limit properties, right? Okay, and the second part, simply because FC is a constant, I can move the FC outside of this limit. Okay, so now you can see both limit, all these terms reduced to the individual limit. Okay, and one is F prime C, the other is G prime C. Replacing both limit will give you exactly the formula we need. That's the product rule. So you can see all these proof are reduced to the it's based. I mean, all this proof is based on the limiting property we established before. Okay. Okay. Now let's move on to the part D. That's a quotient rule. Quotient rule, I know that I have to assume that GC not equal 0. Okay. So we're going to show that G over F over G. I mean, I'm going to prove this quotient rule. It looks complicated. And so first, I'm trying to simplify it. So instead of proving this full quotient rule, first we are going to show a simplified rule. That means replacing the function f by just a constant function 1. So that means you plug in this f by 1 there. You can see derivative of 1 equals 0. So therefore, the right side becomes G prime C over GC squared with the minus sign. The left side is 1 over G, the derivative of 1 over G, okay? So, and we claim that in order to show the full quotient rule, and I only need to show D prime, okay? A simplified quotient rule. Why? Because D prime combined with the C, that's the C is a product rule, together what implies the full quotient rule in the part D. So I can show you why. You can see F divided by G can be written as F times 1 over G. Okay, so if you regard F divided by G as F times 1 over G, then you apply the product rule, and this will give you two terms. The first thing F prime times 1 over G. The other term is F prime times the G prime C. Okay, now suppose I can prove the D prime. Okay, suppose D prime is proven. So then in the second term, there 1 over G prime can be replaced by what? By FC and G minus G prime over G squared. Okay, and now if you put in these terms together, I mean the first term, that there's both fraction. So the first time I have to multiply GC, okay, on both sides. So you'll get this formula you'll get exactly the quotient rule. Okay, so if we borrow the product rule, we just proven in part C here, and now the question is just reduced to show the simplified quotient rule. Okay, just 1 over G prime equals to minus G prime divided by G squared. So that's the things I'm going to show you how to do it. Okay. So now we reduce to show the D prime. Okay, 1 over G prime equal to that. So again, by the assumption I know the limit for G, right? So then I look at using the derivative concept applied to the G prime, 1 over G. So we want to show 1 over Gx minus 1 over Gc divided by x minus c. Okay. Now on the top you have two fractions. Okay, two fractions that are different, of course, and you can combine these two fractions together, right? Then you end up with a new fraction, which is xx minus gx minus gc on the top. Okay, then the bottom is x minus c, then gx gc. I think I missed the minus sign here. There's supposed to be a minus sign there. Okay, and so yeah, in the next step, you can see the minus sign there. Okay, and then I can see this complicated fraction can be considered as a product of two things. One thing is gx minus gc divided by x minus c. So that's one thing. The remaining part is 1 over gx gc. Okay, so so you can think about the previous limit as a limit of these two things together, is a product of these two things. And then using the limit property. So this limit of product can be reduced to the product of limit. Okay, now you have an extra minus sign there. Okay, now you're taking limit. If you take a limit, you can see that so the second, the first limit corresponds to g prime c by the derivative concept, and the second one, and as x goes to c, so you just get 1 over gc times gc. That's the gc squared. Now, since gc is assumed to be not equal 0, so therefore, so this formula works. Okay, so that's the quotient rule. Any questions? So far we have proven these two rules, and these two rules are critical when you have to use them to compute the if you have a specific function, normally you have to use this rule to compute the derivative, right? Okay, so you all know how to compute this in Calculus 1. Here, we are providing the theoretical result about the theory behind these rules. Okay, now if you remember that in Calculus 1, we are not just studying these computation rule, but also you study another rule. It's called the chain rule. It's called a chain rule. Chain rule basically saying that you have a composition function, g circle f, or you can say this is a f gx. Okay, so the derivative is actually is a derivative of g composed with f times the derivative of f prime, the derivative of f at the same point c. So this is called a chain rule. So here, so in the chapter 1, we actually we didn't prove this exactly. I mean, give a series proof of this quotient rule. But here we're now giving a series proof of this rule. Okay. Now there's an example. Suppose you want to compute sine 1 plus x squared, and for function simple function like that, you have to use chain rule, right? It's become cosine 1 plus x squared times 2x. 2x is the derivative of 1 plus x squared. So the chain rule is so important. So combining chain rule and also the previous 4 rules together, you are able to compute the derivative for the many different kind of functions. Okay, so we're now in a position trying to prove the chain rule. Okay. Okay, sorry. So what we're going to do here is we're going to define a new function. So let h be a function defined by the following: hx equals to the quotient of the composition functions. Okay, then you can gfx minus gfc divided by fx minus fc. Okay, now this thing is complicated because you cannot control whether this thing makes sense or not. Because if fx not equal to fc, then the bottom of this expression is non-zero. So this fraction is valid. But when fx equals to fc, then this expression is not valid because you cannot divide by 0. But the question, you don't know when this is going to happen. Okay, so of course I know that when x equal to c, then fx should equal to fc, right? But it may happen that when x is not equal to c, but however fx still equal to fc. So there's no control of this expression. Okay, so therefore when we define this quotient hx, called hx, I have to assume that this expression is defined for those x for which fx not equal to fc. But also we want to here dealing with a case when fx equal to fc. So what we should do? So I'm going to just give it's a special way. I mean, and then I can see that now fx is C is actually equals to G prime FC. So the correct way to think this is that if fx equals to fc, okay, if fx equals fc, then fc and it's just equal to G prime fc, okay? So this h is a function defined this way. And then it's easy to see that as x goes to c, and gx is equals G prime fc. Obviously, this limit holds, of course, okay? Because you can check the, so this again follows from definition of the G functions, okay? Okay, now keep this in mind. So now let's continue, okay? So we have the following, okay? So if we manipulate this expression, you can see that fx minus fc times the gx, hx. Now and remember the previous hx having fx minus fc in the bottom. So if you times the fx minus fc to h, then the bottom things canceled. So this will give you g of the fx minus and the gfc. Okay. All right. So then I'm going to take a limit on both sides. Take a limit on up. Now, first I'm going to divide x minus c on both sides. Then I take a limit. So then you can see the left side consists of a product of two terms. The first is a limit of the fx minus fc divided by x minus c. The second is a limit for h. The right side is limit for the quotient of the composition functions. Okay. Now remember our definition h, okay, it's defined this way. Also remember that we know that the limit hx is equal to G prime fc. So therefore, if you re-examine the above formula for the limit formula, you can see the right side, the left side is just equal to f prime c times G prime fc. Okay, and the right side is just equals to the derivative of the quotient, the derivative of the composition function. So this is how we so this is the correct way to prove the chain rule. Okay, the chain rule. So this is all I have to cover today. So so we're going to have 4 homework. However, basically I'm assigning 3 homework because I'm going to tell you, I'm going to show you how to do the first homework. Okay, and what you are going to do is the number 2, 3, and 4. The number 2 is very simple because you have a composition case using chain rule. So they give you all the result, all the data here, and you can compute the derivative of the chain of the composition function. And the number 3 is you want to show that the derivative of f at some certain point can be re-expressed in this way. Can be expressed this. But however, you have to be careful because only when the f has limit, the derivative exists at this point, then this derivative can be written in such a way. It means that if the derivative does not exist, okay, then the right side may not make sense. The limit still makes sense, but however, the function may not be differentiable. So that's number 4. You have to give a counterexample on that. Okay. Okay, now let's look at number 1. So number 1 it's complicated, it's strange. So that's why I'm going to work with you together. Okay. Homework number 1. So we have a function defined like this: fx equal to x squared times sine 1 over x. Now in the previous chapter, we talked about sine 1 over x. Okay, sine 1 over x. We know this is this function at 0 carries a very special discontinuity. The function is discontinued at 1 over at x equals 0. So this function is defined to be x squared times sine 1 over x when x not equal 0. Because when x equals 0, this expression doesn't make sense. You cannot talk about 1 over 0. But however, we can define f0 equal to 0. So you can see that this function is well defined for all x. okay, for all except that you use two formulas to define. Okay. Now, when x is away from 0, then this function carries a very nice expression, just x squared sine 1/x. So everything's smooth, so the function is differentiable, okay? But however, at 0, when x equals 0, this function is defined by another formula that's just by constant 0. So therefore, by looking at the expression, the previous expression does not tell you anything about what happened at the 0, whether the function is discontinued or what at 0, or differentiable or not. And we don't know. But however, this is something we want to examine. So we're going to show that now obviously f is differentiable for all x non-zero, for all non-zero x, okay? Now when x equals 0, we have to use the definition. This means that you have to you have to begin with f prime 0 by limit fx minus f0 over x minus 0, right? This is followed from the definition. And you plug in f. So when x is not equal to 0, the expression is x squared sine 1/x. Then f0 equals to 0. So plugging all this information there. So you have 2 0 on top and the bottom. And then you can see that get rid of 0, the x cancel, one of the x will cancel on the top. So you'll end up with the limit x sine of 1/x. And this guy carries, the limit exists, is equal to 0 because x, when x goes to 0, x will go to 0. And sine 1/x is a bounded function. It's bounded by 1. So therefore, the whole thing will still go to 0. So this shows that at x equals 0, the function is also differentiable with the derivative at 0 equal to 0. So that's the result of that. But there's a second part of the second part of the problem is to show that actually, even though the function is differentiable at every point, including 0, but however, the function is not, the derivative of the function is not continuous at 0. Okay, so the second part. So thinking about x is away from 0, and I have a nice formula. I can compute the derivative using the product rule and also the chain rule, right? So I can compute the derivative f prime by this formula. That's 2x times sine 1/x plus x squared times cosine 1/x times the derivative of 1/x. That's minus 1/x squared. And then you can see on the second term, x squared cancel. So the derivative of this function at x is equal to 2x sine 1/x minus cosine 1/x. Now, this is the formula of the derivative for non-zero x. I mean, assuming x is away from 0, okay? So what we need to prove from here is that this derivative, okay, when x goes to 0, it's not going to approach to 0. Okay, so the previous computation showed that the derivative at 0 equal to 0. This is something we know. Now we got a derivative at other point. So when this other point goes to 0, if the derivative goes to 0, then this will mean the derivative is continuous 0. But what we need to show that when x goes to 0, the derivative will fail to go to 0. Okay, why? Now you take a limit on this expression. Now first term is 2x sine 1/x. I know that the limit equals 0. But however, the second term is cosine 1/x. Now that thing has, the limit does not exist. Non-existence, you get non-existent. The limit does not exist. So therefore, from here, you can see that the derivative, the limit of the derivative does not exist as x goes 0. This is because the cosine 1/x is not continuous. It's not continuous at the 0. Does not exist. Okay, and you can see the picture. The cosine 1/x, just like sine 1/x, is highly oscillated near 0. Okay, when x goes 0, this guy does not go to 0 at all. Okay, so that's the whole number 1. So the homework number 1 will tell you that when the function is defined piecewise with a different formula, then normally when you compute the derivative, you have to apply the the definition of derivative to get there. Okay, so this is all I have to say. Okay, so trying to work on the homework problem number 2, 3, and 4. And next time I'm going to review this homework with you. Next time we'll continue from here. We're going to talk about the another important area of the differentiation. It's called the mean value theorem. There's a group of important theorems there. Okay, any questions? Okay, if no question, then we can stop here. And so that's it for today. Okay. Thank you.